I want to introduce our presenter at noon, our keynote speaker, Ryan Callahan of Tech Environmental. And we've worked with his firm. They do work for communities, they do work for developers, they do work for all different kinds of folks. Their technical expertise on sound issues have been really helpful and useful in being able to document and put in clear and understandable language the issues of sound and flicker. And so we thought there's been enough discussion about those issues that we should bring in Ryan for a keynote presentation this year so that we can go about the business of trying to better and more clearly understand not only what we're talking about, but what we're hearing. You're welcome.
Good afternoon, everyone, and thank you for giving me some of your time today. Well, maybe you don't have a choice, the door's going to be locked. Thank you for that great introduction, John. It's true, I'm a sound guy. I've spent the last decade plus modeling and measuring the sound of wind turbines. And the monitoring process in particular is really quite difficult and involves being very stoic and standing very still and making no noise of your own and using your ears to document what you're experiencing. So some people might say I'm a good listener. Just don't ask my wife that. A little brief Acoustics 101. I apologize that it comes right after you've eaten. I know some of this stuff isn't the most exciting to talk about, but in order for the rest of the presentation to make sense, we really have to touch base on some of the terms that we use as acoustic professionals and different weighting networks and what decibels are. We'll move along to talk about the question that I've asked more than any other. Are wind turbines loud? That's one of the first things that people ask me when I tell them what I do. They say, well, are they loud? How many people in here have been within 1,000 feet of a wind turbine? Quite a few. How many people have been within 500 feet of a wind turbine? All right, so a little less. How many people have walked right up underneath the tower and stood directly underneath it? So that's good. That's more than usual, which is good. Just you have an appreciation for what they sound like and the volume level that we're talking about here. We're going to move on to turbine noise complaints. When people complain about the sounds that they hear, is that a health issue, or is it really just a question of being annoyed by what they hear? And then sort of a bonus category at the end, if I have time, we'll touch base on shadow flicker, because that sort of goes hand in hand with sound. Sound and shadow flicker are the two sort of hot topic issues that always come up when a new wind project is being developed. So we'll talk about options for controls on shadow flicker and sound. So when we talk about sound levels, there's really two types of sound levels that we are generally referring to. One is referred to as the sound pressure level. The sound pressure level is what we actually measure with our sound meters. That's the sound level that you see when you have a sound meter and you're looking at decibel numbers. Sound power level is a totally different thing and cannot be measured, it has to be calculated. And when people mix these things up, it leads to a lot of problems in our profession. A good example is, think of a light bulb. If you have a 100-watt light bulb, everyone can sort of appreciate how bright that is. But when you turn the light bulb on the other side of the room, the light that's shining on you is certainly not the same as if you walked right up to the light bulb and put your eye right against it. So a sound power level describes that sound source's total sound energy right at its source. A sound pressure level requires a distance to have meaning. So if you say something is 50 decibels, that doesn't mean anything unless you say it's 50 decibels at a certain distance. And when you mix those up, there's very drastically different levels that come into play, and people can get very confused about what that means. Both of these sound levels are typically expressed in what we call A-weighted decibels. The A-weighting network is a network that is designed to approximate the response of the human ear. Just like dogs hear high frequency sound better, humans have a certain range of sounds that they're really good at hearing, and then as it gets very low and as it gets very high, that sort of rolls off. We don't perceive that as well. And as we get older, we really don't perceive that as well. And all of these A-weighted decibels, just to give you an idea of some typical things that we may experience every day. What are these decibels, and what sort of range are we talking about? Normal conversation between two people outside on a sidewalk, you're looking at 60 to 65 A-weighted decibels. That's the general sound level that a conversation would be. If you're 50 feet away from a highway and a tractor trailer drives by at 65 miles an hour, 80 decibels is what you can expect to experience from that. So finally, we're going to talk about the LEQ. This is sort of the gold standard sound metric that we use as acoustic professionals. The LEQ is what helps us describe a sound level with a single number. Most sound sources fluctuate up and down, and the LEQ gives us a way to describe that sound without talking about a range of sounds and further confusing all of these topics that we're trying to cover here. So the LEQ level is sort of the average sound level. It takes into account the total, all the energy of that sound source over a given period of time. And finally, the end of the Acoustics 101 here is the decibel scale is logarithmic. So unfortunately, it does not add as you would think. If you have something that's 40 decibels and you have something else that's 40 decibels and you put them next to each other, they do not equate to 80 decibels. It actually results in 43 decibels because of logarithmic math. So that means that when you double the sound of something, you're actually increasing it by 10 decibels. Or if you're making it half as loud, you're decreasing it by 10 decibels. If you're watching your TV and you took the volume control and you turned it up until you thought that you made it twice as loud, what you've done is change the decibel level by 10. So if it's 50 and you turn it up to 60, you would perceive that as being twice as loud. So now we're all acoustic experts. Congratulations on getting through that portion. I'd like to now talk about what loud means to we as acoustic professionals. When someone says that's loud, well, if you look at some synonyms for what loud is, blaring, booming, deafening, roaring, I think we can all agree that if it's loud, it might scare you or make you jump. It has to be a pretty significant sound level. And what is that sound level? Well, there's no magic decibel level that all of a sudden becomes loud. So we as acoustic professionals have to try to define where things fit into the spectrum. So here's an example of two scenarios I think everyone's experienced. On the top, there's a library. If you were to walk into a library, the typical sound level in a library is around 35 to 40 decibels, with the HVAC equipment running and people walking through the aisles of books. On the bottom, two people sitting and having a casual conversation is more like 60 decibels. Now, typical levels experienced from a wind turbine at homes that might be near a project area are in the range of 35 to 45, which falls between these two examples. I don't think either of these two examples would be considered loud, and therefore, the grand finale question, are wind turbines loud? Well, no, they're not loud. They're around 45 decibels, and we just said a library is 40, so they're not loud. I worked very hard on the slide, by the way. It's one of my finest PowerPoint moments. Here's a project that I worked on a few years ago that a turbine was placed between classrooms and athletic fields. The turbine's actually 200 feet away from their football field, and I mean, most of the time they don't even know it's there. Certainly I would not recommend putting a turbine 200 feet from a home, but in this scenario, for daytime use with athletics and classrooms, it works just fine, and there are no complaints about the sound of that turbine operating. All right, on to the interesting stuff. How do we measure turbine sound? Once a project is built, We are often asked to go and document the sound levels that those turbines are making to ensure that they're meeting local regulations and they're not exceeding what we predicted they would be. So in this slide, you see a sound analyzer right front and center, and a great big beach ball on top of it. That's the windscreen. When wind turbines are operating at their maximum volume, there's plenty of wind going around, and as a result, when we try to measure them, we're dealing with that sound, and you don't want to measure that sound, you're trying to measure the sound of the turbine, and this great big windscreen helps us do that. In the background, you also see another instrument on a tripod. That's actually an ultrasonic anemometer that we use to record ground level winds simultaneous to our sound measurements. There are many standards that tell us how windy it can be, and when it gets too windy, you can't take accurate sound measurements, so there's really a difficult time accurately measuring wind turbines. It takes perseverance and lots of time, and it's usually very cold, I can tell you. Before wind turbines are built, sometimes we do a pre-construction sound survey to document existing sound levels. Here I am working very hard in a field. I believe this was in Michigan. We set up a bunch of sound meters and let them run for 2 or 3 weeks to document the existing sound levels before any turbines were constructed, to sort of get the acoustic footprint of the environment. When we do the post-construction monitoring, there are a number of factors that have to line up. I talked about the high winds. Well, yeah, it has to be windy enough for the turbines to be operating at their maximum, because we're not interested in measuring how loud they are when they're just cutting in, they're just starting to spin. We want to find out their maximum sound level, and to do that, we need usually around 10 meters per second is a lot of hub height design wind speeds. And that correlates to a very windy ground level condition. And we can't have intrusive events going on when we're trying to document this, dogs barking and traffic and airplanes, everything sort of contaminates our measurements. So as a result, most of the sound monitoring that I do is done in the middle of the night, which is quite an experience. So as you can imagine, you're out there in the middle of the night trying to measure the sound of this wind turbine, which might be around 45 decibels, and you have all the trees blowing around you, you have the wind going across the countryside, and it's a challenge, but we can do it, and we have done it successfully on several projects across the country. Here's a great photo of me doing some nighttime monitoring. Yep, that's the sun rising. Sound meters in the bottom there. That's pretty much what we see. We stand there for 5, 6, 7 hours, and we document the sound levels, and then we correlate that to what power the turbines were making at that given time. Here's some better pictures where you can actually see us doing it. But on the left, that's actually the moon in the sky there. And then on the right is a setup that we had where we went out there during the daytime, got all of our equipment set up, and then returned in the middle of the night, so we didn't have to carry our equipment through the fields in the dark. So what does some real data look like when we do these studies? Well, here's a graph of sound levels that were measured before a project was constructed. You can see the scattering of points here, and these are 10-minute LEQ sound levels, and everyone now knows exactly what that is because of the wonderful job I did explaining it a few minutes ago. So 10-minute LEQ sound levels were plotted against the hub height wind speeds, and you can see as it gets windier, it gets louder. That's what that green line is telling us, that the wind level increases, the existing sound levels increase. There's no surprise there, but that shows us the challenge of measuring how loud a wind turbine is, because when you're at 10 meters per second hub height, you can see the existing sound levels are typically at or above 45 decibels, and that's usually around the sound level the wind turbine is making. So you're trying to measure something that is being masked heavily by existing sound levels. Here we have the sound levels and the hub height wind speeds plotted against the total sound level of the turbine and background sound, and the level of just the wind turbine. So again, you can see as the wind speed increases, the turbine really doesn't make any sound at all until you start getting closer to design wind speed. And then once it makes its maximum power, it plateaus off and generally stays at the same volume. But the background level just keeps on going up as it gets windier and windier. So we are always hunting this sweet spot of being very windy for the wind turbine, but not too windy for us at the ground. I mean, it's a little tricky. This is a graph showing us how sound levels change with distance to a wind turbine. So there are a lot of people in the room that have been at all different distances to a wind turbine, so you can appreciate what this means. If you're 300 meters away from a wind turbine, well, you're going to be right around 45 decibels. As you go further and further away, it becomes quieter and quieter. There's no surprise there. Now I'd like to sort of change gears and talk about how we predict the sound of wind turbines. So before a project is constructed, we'll do a modeling analysis using some 3D modeling software. And the 3D software allows us to actually put the turbines in the positions that they're looking at, and then calculate what sound levels might be experienced in the project area on a cumulative basis. So this is a particular layout of turbines. Each one of these sections is 1 mile, so you're looking at about a 6 mile by 6 mile area. The black dots represent homes, and there's different phasings of turbines by different colors. The important thing to note with this modeling is it represents the absolute maximum condition with lots of conservatism. So this model actually predicts the sound levels, and it assumes that everyone is downwind at all times, because sound can be influenced by wind direction. Now, of course, if you're looking at this area here, and you have the wind out of the west, you'd be downwind of these turbines. But you wouldn't be downwind of these turbines, but the model is telling us that you're downwind of both of them at the same time. And that's an incredible amount of conservatism that we use in this modeling. So these levels are absolute. I've actually never seen them quite get to what we predicted. It's always usually a little lower, which means that we're doing a good job of predicting with conservatism. Here's an example of several different communities around the country and what their sound level limits are. It's really quite incredible. I've traveled around to many different states and counties, and the sound level limits are all over the place. They're really, they range from very, very low to basically silence, which doesn't really make sense, to nothing at all, which also doesn't really make sense. So this is just sort of an example of what different communities around here that have wind energy set as their limit. And during the process, as we're modeling the sound of wind turbines and working with a developer to sort of tell them what they need to do to meet these limits, there are a couple of options that they have. And there's some new technology that's come out in the past few years that's actually been very good for wind developers. Something called low noise trailing edge blades. And if you've ever seen a pigeon take off, the pigeon's wings it flaps, makes some sound. You hear a pigeon. If you've ever seen an owl fly across the room and not make a sound, and that's because the shape of the owl's wings are serrated, and they have a shape to them that allows them to slice through the air and not make a sound, I guess, so they can catch mice and things. But so wind turbine engineers have sort of stolen that from owls, and some of the blades that they're now using have serrated edges on the back side. So as they cut through the air, they're actually causing less turbulence, and as a result, the turbines are quieter. So this is some exciting technology that has been implemented in several studies that I've worked on. The other options are NRO, noise reduction option, or noise reduced option. Essentially what it does is it limits the spinning of the turbine. It slows it down a little bit to limit the sound. That's another mitigation option that some developers use. And lastly, the upwind turbine is sort of the biggest development. I think a lot of people have a sort of negative idea of what wind turbines sound like if they saw wind turbines in the very early stages, in the 70s and the 80s. The very first turbines were actually downwind turbines, which means when the wind blew, the turbine would face away from the wind. And I sort of liken that to jake braking on a tractor trailer. You're downshifting, it's sort of lagging and pushing on the blades. Turbines aren't like that anymore. Turbines are now upwind and they face into the wind. And as a result, a lot of the low frequency noise that people talk about has been eliminated because they are now upwind turbines. So let's talk about that low frequency noise. Another question I get asked is, what about this infrasound business? Well, infrasound isn't anything special. It's simply a term to describe low frequency sound. The range of the human voice, as you can see, 500 to 2,000, that's where we hear really well. Low frequency sound is below 200 when you hear the bass of a car driving by with the stereo blasting. Infrasound is typically thought as less than 20 hertz. Really, really, really low frequency sound that we generally cannot hear. You can hear it if it's high enough, but the levels that it would need to be are rarely seen anywhere in the world unless there's some scientific experiment specifically designed to create infrasound. And there was a scientific experiment to create infrasound. It was performed by NASA. Essentially, they were looking at what effect infrasound would have on people that would be in the space shuttle, because that makes quite a bit of infrasound when a shuttle takes off. So what they did is they put these young men in a room and they basically exposed them to outrageous levels of infrasound for a very, very long time. And that was an interesting article to read, but it really doesn't have any relevance in any other industry, because I don't think anyone here is getting on the space shuttle anytime soon. But at some levels of infrasound, you actually are able to start feeling it. It actually starts moving your ears and things. But that's millions and millions and millions of times louder than the infrasound produced by a wind turbine. So when people talk about infrasound, it's really a non-issue because it doesn't generate enough infrasound to be a factor. If you've ever been to the beach and you saw a wave crash on the beach, you've been exposed to thousands of times the infrasound that a wind turbine could produce. The wave crashing on the shore, you hear that thump as it hits. You're hearing the thump, you're hearing the low frequency. The infrasound is actually lower than that, and you can't hear it, but it's happening. And if you sat on the beach all day, you've been exposed to way more infrasound than any wind turbine could ever produce. So that's just something to think about. So these are just the summary of the infrasound produced by wind turbines and how it relates to our hearing threshold. And here is a spectrum that we plotted of, again, actual measurements. This was a wind farm in Michigan again, and we took measurements without the wind turbines operating. And you can see this is sort of the frequency spectrum from the wind. And then we've plotted on top of that the predicted frequency spectrum of a wind turbine. And you can see that the low frequency sound being generated by the wind alone is actually the same or generally higher than what you would get from a wind turbine. So just the sound of wind passing by a landscape can generate more infrasound than a wind turbine. This is another example. This is in a totally different state. This is in New York. It's the exact same graph. And again, we see the exact same results where the infrasound generated without the wind turbine operating is at or above the wind turbine. So my conclusion on infrasound is basically, I don't quite understand why it's an issue, other than it sounds scary when you see the word infrasound, but when you understand what it's actually talking about, there's really nothing to be frightened of. It's just low frequency sound. It's happening all around us all the time, and we've all been exposed to it, and there's nothing nefarious or different about infrasound than other frequencies of sound. It just has its own name, and because of that, sometimes people associate that with something special. It's really not. So I'd like to move on now to when we get complaints about the sound from wind turbines, are the people that are hearing these wind turbines, are they actually being physically harmed by the sound from the wind turbine? Well, we can look at some studies that have been done recently. This study was done by the Massachusetts Department of Public Health. What they did is assemble a panel of epidemiology experts, toxicology experts, neurologists, doctors, mechanical engineers, and they sat down and they reviewed all of the literature that was available on wind turbine sound. They did their own research and own measurements, conducted interviews with people that live near wind turbine projects. And this is what they found. They concluded that there was no evidence for any sort of health impacts from the sound of a wind turbine. So although people may have complained and said, I can hear this turbine, they concluded they were not being physically harmed and it was not harmful to their health. This idea of wind turbine syndrome was basically has been dispelled by the health officials. And this is the key findings from that one particular study. They also looked at infrasound and they concluded the same things that I spoke about earlier, where it's not a concern. There was another study done, similar to the Journal of Occupational and Environmental Medicine. They did a similar study where they reviewed all of the literature on wind turbine sound, and they had the same conclusions where they couldn't correlate the sound from a wind turbine to any sort of disease or health impact. It was basically that people were reporting annoyance from hearing the wind turbine, but they were typically the ones that were not benefiting financially and were not. I think the story sort of tells itself there, but and again, they also concluded that infrasound does not present any health risks. There were a few other studies done. I'm not going to go into all of them, but Health Canada did a similar study, and they had years and years of data that they analyzed, and they concluded the same thing, that sound from wind turbines does not cause a health impact. And again, why would it? We saw that it was slightly louder than a library and quieter than conversation, so if that causes a health impact, then we'd all be in trouble. Now, there are other studies out there. The danger of the internet. If anyone's ever felt sick and gone on WebMD and typed in your symptoms, you can see that you have every disease imaginable. And that's a similar thing with wind turbines. It's unfortunate, but it is what it is, and we, as acoustic professionals, have to sort of confront it and talk about it, because the studies are out there. There are studies that say these wind turbines are making me physically ill. They're giving me headaches. They're giving me double vision. The problem with these studies is they all have many, many, many fatal flaws. In the engineering and scientific community, there's a proper method for carrying out a study, and none of these studies do that proper method. So as a result, they're really not credible. There was one particular study, the Cooper study, we run into it all the time. The interesting part about this study was they say right up front in the study that many of the participants are anti-wind people. They don't want wind, they don't want to see it, and that's fine. Everyone has the right to what they want to see and experience, but I don't think they should be part of a study to talk about the effects that it's having, or if they are, at least have a control group of people that are not self-admitted anti-wind folks. It was not peer-reviewed, which is another fatal flaw of any study. You can't just do a study and then present it without having the scientific community vet it. And I think the most interesting part of this study was that the people were asked to document when they felt impacts from the wind turbines, and a lot of people were documenting impacts from wind turbines when the wind turbines weren't even spinning. So unfortunately, that doesn't really sit well with me as an engineer and with most people when they say, well, I don't feel good that the wind turbine is bothering me again, and then they looked at the time and said, well, the wind turbine was shut down that entire night, so I have a little issue with you saying that it is causing you physical harm. Finally, I'm going to talk about shadow flicker. Shadow flicker is what occurs when the sun is either is rising or setting, is very low on the horizon, and the turbine is between the sun and where you are. So the blades will cast a shadow and momentarily block the sun for brief periods of time under a certain set of conditions. The conditions that have to happen for shadow flicker to occur, it has to be sunny, obviously. So if it's cloudy, there can't be any shadow flicker. The turbines have to be spinning, so if it's not windy, there can't be any shadow flicker. And you have to be close enough to the turbine with the right angle of the sun. And depending on the time of year, that angle of the sun varies quite dramatically. And usually what we see is it only happens in one specific time of either early spring or late fall. We also do modeling to show the impacts of shadow flicker, so when people are siting wind turbines, we can show them where they should position them to reduce the impact of shadow flicker. So this again is a contour map showing predictions of how much shadow flicker will occur per year. And these lines are 10, 20, 30, and 40 hours per year. So, and that's with all those factors lining up. So this is, again, a very conservative approach. You can see they sort of look like little butterflies. That's just an artifact of how the sun rises and sets. The flicker, when it does occur, it occurs, it's slow. It's a slow flashing. It's not a strobing that's very fast, so it's not a concern for seizures. Some people cite that it can cause seizures. That's not true. It's also rarely regulated, although we do look at the impact of shadow flicker and we try to provide better sighting to avoid it when we can. There's typically not any regulations, so that I think could be improved. It's also very easy to control because you can simply turn the turbines off for the 30 minutes a day that the shadow flicker occurs, and that has been done in many wind sites around the country. Also use of screening, planting trees. If you already have trees, it's not going to occur because the light is not going to be hitting your home. But the strongest mitigation for shadow flicker is just to have a very good project layout from the get-go. And that's what we try to do. All right, well, thank you for listening to me today, and I hope everyone could hear me. There's nothing more embarrassing than not being able to hear the sound guy. But if you have any takeaways from my presentation, I would like you to know that wind turbines are not loud. Infrasound for wind turbines does exist, but it is inaudible and it is not a health concern. And that there are a variety of new technologies that's continually making the wind energy sector better and better with regards to both sound and flicker. There's low noise blades, and the mitigation programs are really, they're good things, and it's getting better all the time. So with that, if anyone has any questions for me, I'd be happy to answer them.
Questions?
Thank you, Ryan. Dave Bachowitz, Linn County Wind. One of the questions on the infrasound, and we've been hearing a lot of that lately because it's on the internet. Nobody heard of it before. But what about the pressure or the pulses from as the turbine is, the blades are spinning, and now you've got a short period of time when the wind does not actually move through the blades, so you're left with a lack of wind movement. So they would have that. How far downwind does that, can that be felt, or do you know before it's dissipated in the swirling of the air? And what effect, where it's not an infrasound like the sound of the wind rustling through the weeds or the trees, but it's just a lightening and lessening and heavy pressure on a person. Thank you.
Sure, so I think there's a couple different questions in there. What you're referring to is amplitude modulation. That's a fancy, again, another fancy term that we engineers like to name things. And it essentially just means the change in sound level. So what you're referring to as the pulsing and pressure, what actually is happening is it's just the change in total sound level. So if you had a stereo and you turned it up and you turned it down, and you turned it up and turned it down, the sound level is just going up and down, and that's what amplitude modulation is. So as far as how far you have to get away from it, did you say, to not be able to perceive? Is that?
You're kind of mixing up two things. Think of it more instead of volume up and down. A truck is between me and the wind source, and then the truck moves, and all of a sudden I feel the wind. Now another truck comes by, so the wind is being blocked, and then it's not being blocked. So you've got pressure and no pressure, no pressure as the blades revolve.
Right, but that pressure, that's sound level. So the sound level is going up and down, and that's the sound of the turbine. The same thing. It's the sound level that you're referring to. It's the amplitude modulation of the turbine.
How far does that dissipate? If I'm standing next to the road, I'll feel the trucks. But if I'm 50 feet away, I don't feel it anymore.
Right. So you don't feel the sound from a wind turbine. That's an important distinction. You're talking about actual wind from a truck driving by you, like a pressure wave. That's a different animal than sound from a wind turbine. A wind turbine is making sound, and it's modulating that sound with the blade pass frequency around the tower. Sorry, that didn't.
I'll talk to you off.
Sure.
One more question.
I'd be willing to subject myself to a test. In college, we had a class for sales, and our sales teacher pulled out of his pocket a device similar to my pager. He cued it. Anyway, it was a very high-pitched squawk. And the device was for when the salesman pulled into your yard and a dog was attacked you, you'd key it and the dog would run off. I could hear it. I about fell through my chair. One of my classmates said, I thought I could hear it. Anyway, we get done with class, we walk outside, and Bruce, my instructor, behind the keys, and I turned around and about grabbed him. He said, you weren't kidding? I said, no, I was not. I could hear it. The flip side of the coin is my dad was the other side of the equation. Low tone noises drove him crazy. I mean, it just bugged him no end. We got me running the buzzsaw, sawing up firewood. That ringing of that saw just drive me wild. I put in earplugs and hear it all. Something else that would bother Dad, I couldn't even hear it. Like I said, I'd be willing to subject myself to the test in the sound chamber or something, a really high pitch, to see if I could still hear it. I would, and I'd be willing to share the results with the group. But I must be wired a little different than somebody else.
Yeah, there are a small percentage of the population that has more sensitivity to a wider frequency range.
Mine would be high end, my dad was way down to the low end. Maybe that's where
got it all covered there.
My dad's no longer with us. I wish he was to be subjected to the same test. Because I think part of my dad's situation was he was in World War II, he was an aircraft spotter. The constant low drum of a bomber or something, maybe is where he picked that trait up from. I don't know. I wish we were still here to do the test on it. I used to think Dad's crazy. And half the neighborhood thought the same. And I've come to appreciate the fact that maybe my dad heard a whole lot different than what I did. Because what drove me nuts, he couldn't tell it at all. And that's maybe where very few of these folks on wind turbines, the low drumming noise would give. Maybe there's, out of maybe there's 10 people that would pick up on this. It's something to think about, in my opinion. Thank you.
Thank you.
All right, we're going to need to bring this to an end, so let's give Ryan a big